Okay, so I know there were some questions about the chi-squared test, all right? And so, the way the chi-squared test works is you get basically a vector of, I don't know, observations, right? So, 20, 30, 40, okay? And you want to compare this to some vector of probabilities. So, let's say you hypothesize that the proportions should be 30%, 30%, 40%. Okay? So they need to add up to 1. So you hypothesize that you've got 3 different categories. Your hypothesis is that category 1 shows up 30%, category 2 shows up 30%, category 3 shows up 40%. When you went and gathered your data, you got 20 of category 1, 30 of category 2, and 40 of category 3. And so now the question is, could these results have happened by random chance, or is this an indicator that the data is coming from a distribution that's different from these stated proportions, right? This sounds kind of familiar, all right? The chi-square test. So you just do chi-square test, and you compare your thing, and you say the proportions is p, okay? And it says you get the chi-square test for given probabilities, and here we get a p-value of 0.273. So we would say, okay, we do not have evidence that these observations, 20, 30, 40, is coming from a distribution that's different from 30, 30, 40%. Okay? But for the chi-squared test to work, there's an underlying central limit theorem hypothesis, and one of the conditions for it to be valid is that the expected proportions all have to be over 5. The expected counts of probabilities, right? So in our case, we observed a total of 90, right? And so if any of my proportions was, less than 6%, right? So if my proportions was, let's say 30, 30, 35, and 5%, okay? And then I say my observed counts were, let's just say 25, 35, 35, and 6, okay? Then when I do my chi-squared test, and I compare D to these given probabilities, I guess it didn't, let me see. Oh. No, this adds up to be more than, let me just change this. Okay, 20, we'll do 20, 30, 30, and 6. Okay? So because if I do sum of D is 86, and if I multiply that by 0.05, the expected count for one of these cells is only 4.3, right? So if I do a chi-squared test between D and P, it says the chi-squared approximation might be incorrect, right? And so what we have to do here is we take a look at our P, and we might have to combine some of these so that none of the proportions will give an expected probability less than 5, okay? And so if you're testing out kind of the binomial distribution, some of the values towards the extremes will have expected, will have probabilities close to 0, and will have an expected count close to 0. And so you might have to kind of just put some of those probabilities into one of the other groups. So in this case, we probably have to modify P to be 30, 30, 40. So so I'll just combine these last two, and I'll do 0.3, comma 0.3, comma 0.4, and then my D, I would have to combine these 6 back into here. And so my D would be 20, 30, 36, okay? And then I can do my chi-squared test of D versus P. And now the error goes away. So you just, for the chi-square test to work, you need a vector of counts of each category, and then you need a vector of probabilities for each of those categories. And so the vector of counts needs to match the vector of probabilities as far as lengths go, and the vector of probabilities, you don't want any one value to be super small, such that, you know, n times p for that category would be less than 5.
How do you do the combination?
How do you do the combination? I mean, all I did, I did it manually, okay? I said, what did I say? I said, you know, the probabilities are 30, 30, 35, and 5%, and because the total counts, my sum of D is 86. 86 times 5% gives me a value less than 5, okay? And so what I need to do is I need to kind of just get rid of this one that's only 5%. And so I arbitrarily just put the 5% into this one. You know, if you had an actual categorical variable, you'd probably want to try to think, you know, which categories make sense to combine. And maybe it doesn't really make sense to combine, but, you know, you try to combine ones that make sense. In terms of the binomial, your categories are actual counts. So it makes sense to combine adjacent counts. So, you know, if...
On the homework,
So in the homework, I think I asked you to, what did I say? N is 10 and P is 0.4, right? So in this case, if we do D binom for 0 through 10 with size equal to 10 and P equal to 0.4, these are your vector of probabilities, okay? And your expected counts will be that vector of probabilities times 200, because we're doing 200 samples, right? So these ones in the middle are okay, but these ones have expected counts less than 5, right? So this one over here has an expected count less than 5, and these ones have an expected count less than 5. So in these cases, we would want to kind of combine this into probably the adjacent one. So instead of saying, how many times do I expect to get 0 and how many times do I expect to get 1, we're going to say, how many times do I expect to get 0 or 1? And it would just be, you know, we add these two together. And then over here, it's, you know, 1, 2, 3, 4, 5, 6, 7. And then it would be, how many times do I expect, instead of saying, how many times do I expect to get 7, 8, 9, 10, it would be, how many times do I expect to get 7 or more? And so that would combine 7, 8, 9, and 10 together, okay? Because, you know, with 200 trials, we don't expect to get 10 heads ever, okay? And we would expect to get 8 heads maybe only twice. So instead we will just say, you know, 7 or more, and that's going to combine these 4 categories into one, so that no category will have an expected count lower than 5. Yeah?
So if our frequency table doesn't have, like, for example, a 0, then you're not actually combining, you can't actually combine 0 or 1 later.
Yeah, so, you know, here, let me just do this. So I'll do R binom. I want 200 values. Size is equal to 10, and P is equal to 0.4. Okay, so this is kind of my output. So this is my out, right? So this is a new set of output. Okay, so these are my outputs, and then I can just tabulate the output. Okay, and so I have, you know, 0 happened 5 times, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so for this to work, I would have to, I don't know, probably as.integer. We'll have to do this. Okay. So I've got this, and then now I have to combine kind of these two together, and so I don't know. How do I do this? So x is going to become x minus the first one, and then the first one of x will be 14 now, right? So this is kind of just manual mode. And then over here, I would combine the 8s with the 7s, and then So I do the same thing. I just drop the last one. I would say the last one. So this is 1, 2, 3, 4, 5, 6, 7. So the 7th one is going to be 9. Okay, and then we just drop the last one. So okay, and then so there's our vector. And we can just make sure that we still have 200, and then we can do a chi-squared test between x. Oh, and then so now my probabilities. D binom. So P is D binom, what, 200, no, not 200, 0 through 10, 10, and 0.4. So this is my P, and then now I have to say P sub 1 is going to be what? Sum of P sub 0 and P sub 1, okay? And then we'll, so we'll drop, do that? Oh, huh? Oh, not P sub 0, P sub 1 and P sub 2, you're right, okay. See, I'm, now, shoot. See, I can't, okay, let's redo this. Okay, so P is this, and then we're going to do names of P to be 0 through 10, okay. Okay, so now I can do this because I can't keep track otherwise. All right, so it'll be P of 1 is going to be sum of P0 and P1. Okay, and then so that works. Okay, and then we can get rid of, and then we'll do P of the 7th one is going to be sum of P, okay, well, this is too tedious here. Okay, 7P, 8, 9, and 10. Okay, and then we can drop the first one, and then drop the last 3. This is 8 through 10. Okay, so there's our vector of p's. This is our output vector x, and now I can do a chi-squared test, x versus p equals p. Okay, and then so when we do that, I get a p-value of 0.628, indicating that I have no reason to doubt that my data did not come from the binomial distribution.
How did this result compare to the one that's not incorrect?
How do we what?
How does this result compare to the result that made it incorrect when the expected value is less than 5? Remember when the expected value was less than 5, it just gave a warning message, but it still gave the p-values and the chi-squared.
I don't remember what it did. Basically, it should also so what happens there is when you have all of those extra categories, you have a higher degrees of freedom in your chi-square distribution, and so that's going to alter, like, because probably your chi-squared test statistic will end up being approximately the same, right? Because you're going to, and the test statistic is observed minus expected divided by expected, right? And so your observed is probably still going to be around the same because your observed is going to be like 0, right? And so you're doing this, and then and it'll probably affect your chi-squared test statistic a little bit, but what it really affects is your degrees of freedom. You're going to have if you've got binomial 10, 11 categories, you've got 10 degrees of freedom, and so that changes kind of where the tail goes, and your p-value might be larger or smaller than what it should be. Yeah. So that's, I mean, you know, if your p-value is 0.6, it's probably not going to make a huge difference, but it might make a difference when you're towards the tail. And so, you know, these are all warnings, right? With when you do a test, you want to make sure that your assumptions for using that test are met. Otherwise, why bother, right? If the test is going to spit out the wrong answer, don't use it. So, okay, that took way longer than it should have. Okay. All right. Well, so I wanted to cover this. I guess I'll just say this thing exists. All right. So we've talked about rejection sampling, right? So as far as rejection sampling goes, so I do expect you guys to be able to do rejection sampling, and I guess we'll talk about the midterm exam as the midterm exam approaches, but I might ask you to do this table's killing me, some rejection sampling, and the idea here is you've got some distribution. Maybe it looks like this. Okay, this is our target distribution. And then you have a proposal distribution. The proposal distribution, the kind of the easiest case to understand is if the proposal distribution is uniform, but the proposal distribution can really just be any distribution where when you multiply it by some constant, it's always bigger than the target distribution, okay? So this is our proposal distribution. It ideally is easier. Proposal distribution, always needs to be larger than the target distribution. And in order to not waste samples, well, here let's just talk about how this works. We then, you propose a y based on the proposal distribution. Okay, propose a y. And you accept y with probability of, kind of the ratio between the height of the target distribution and the height of the proposal distribution after you've modified it, right? And then accept y. With ratio basically target PDF divided by, m times the proposal PDF. And that's it. Okay, that's rejection sampling. For if we don't want to waste the y's, we don't want to propose too many y's that are going to get rejected, right? Okay, we don't want to propose many y's that will be rejected, and so what we're going to do ideally is m is just big enough so that the max height of the proposal so that the proposal distribution is still always larger than the target distribution, but not any bigger than that. Okay, so so we want m so that m times the proposal PDF is always greater than the target PDF. Okay, but not any bigger than it needs to be. that all right? So that's kind of just regular old rejection sampling. We have adaptive rejection sampling, okay? It's not mentioned in our textbook, but it's mentioned on Wikipedia and other texts, okay? And so I'll kind of describe how it works, and we've got some clunky code that kind of demonstrates how it works, okay? So the idea here, so we've got as far as adaptive rejection sampling goes, okay, let's say this is what we want. Let me okay. Let's say we have this, all right? Let's say this is one of the things about adaptive rejection sampling is it says that we want to often work with the log PDF, okay? Log of the PDF. So let's say I want to do the normal distribution, okay? So the normal PDF is kind of in the form of a constant times e to the negative, basically x minus mu squared. If we just use I'm going to just say another constant here, all right? So the normal PDF is kind of in the form of e to the negative x squared. And if I take the log of the normal PDF, I just get negative x squared, okay? Plus some constants. And so let's, well, with adaptive rejection sampling is we can work with the log normal PDF and then exponentiate it to get kind of our regular old PDF, and then we can draw samples from it, okay? So here's the idea here is that we're going to create a piecewise linear envelope, okay? So our proposal distribution is a piecewise linear function. And so, you know, maybe we will, let's say I just start off with something that looks kind of like this, all right? So this is my first and what we do is, you know, at the next iteration, okay, if we accept a value, that's great. Proposal distribution is a piecewise linear function. This makes kind of drawing samples from it easy. Okay, so drawing samples from this function is relatively easy. You know, we can just use inverse Cdf method for this part. And the adaptive part comes from if we propose a value and it gets rejected. Okay, we can then use that value to tighten our envelope. Okay. So let's say I propose, a value right here, okay? And so, it gets proposed because it's above the curve, it's going to get rejected. So what we do here is we say, okay, we're going to find kind of this value here, and we'll find the line tangent to it, and we'll use that to adapt our envelope. Okay, so we say, okay, this goes right here, and then we draw a line tangent to that, and so now okay, and so now my new envelope is a lot tighter to the kind of log PDF here. The eraser is acting all funny. I don't know. Okay, so this becomes our new envelope. Yeah, so now we still have a piecewise linear, and we keep, every time a new point gets rejected, we can tighten the envelope so that fewer and fewer samples will get rejected. Okay, so we're kind of creating a linear approximation to the PDF, but we still use the PDF to decide whether or not to accept or reject that sample. And then and that's how we can do adaptive rejection sampling here. Okay, let me so I guess you can read about it on Wikipedia, and then I'll link to some code. So here's this person implemented some code in R. Their example is a lot more complex than proposing from just a plain old normal distribution. Okay, so let me just kind of demonstrate a little bit of how this thing works. Okay, I'm going to just set some boundaries here. Okay, so H here, this is going to be the log of the normal PDF. Okay, so the natural log of the normal PDF, and valid up to a constant. So it's not the actual log of the normal distribution, but it's valid up to a constant. And then to kind of figure out when we do this, we have kind of the where the thing is tangent. We're going to call these the fixed points, and then we want to know where the tangent lines intersect with each other to kind of get our boundary points for where we switch from one linear segment to another linear segment, right? So if this is so if I've got this, I don't know, thing like this, we'll have, this will be a fixed point. So I'll just start off with a few fixed points. So this is a fixed point. So we call these fixed points, and then we have lines that are tangent to it. And we'll need to find these kind of the intersections here. So in the code, this is the the intersection, which the code calls z fixed. So these are the y fixed, we call these y fixed, and then this would be z fixed. And so our piecewise linear log PDF is basically for x less than or equal to our first intersection it will have a kind of, this part will have the it's the line that is tangent to the first fixed point. Okay, so if you remember, line, do you remember point slope form? Okay, so it's going to be kind of like y minus y0 is equal to m times x minus x0, except so I think in this thing we have h of y, so we go, so this is kind of in the form, so we all have so this, we have the line that's tangent here. It's going to be kind of h of kind of our value. What is it? y0 plus the slope is h prime at that point. Let me see. Let me check the inverses here. H of kind of y0 times basically y minus y1. So that our first fixed point. Our first fixed point, first fixed point. That's what we have over here, and then we add on the intersection. Okay, so this is just the line that's tangent to the first fixed point, and then for between each subsequent thing. So this is kind of for x here, and then x between boundaries. Between kind of our z fixed first intersection and our second intersection. For x between these intersection points, you have basically another linear equation. And so on. Okay, so we have a piecewise linear function here, and it's kind of calculated in these things here. So we have the function for the basically the log PDF, derivative of the log PDF. This thing calculates where all of the intersections are. Okay. So z fixed says, okay, we're going to go through and find where all of these intersecting points are. Okay. And then this function, h plus, is a function that plots out the piecewise linear. So let me just kind of show you what this looks like. Okay, so if I have I'm going to just plot from -3 to 3, and if I calculate the log PDF of that, I have a parabola here. Okay, and now I'm going to add where my fixed points are. I'm going to choose 3, 0, and 3. Okay, and we find the tangent lines for this, and if we and that's going to be the equations of the tangents lines are found using the function h plus here, and if I plot those, this is kind of my envelope function from -3 to 3. Okay, so this is, we're going to use the piecewise linear to propose values, and then we can use that and update this to you know, adapt our proposals. Okay, and so if this is what we have, then we can generate the inverse CDF, right? And so this is the log of the PDF, so the actual PDF is going to be this thing exponentiated, okay, which looks funny. Okay, if I exponentiate, let me just show you what, when I exponentiate this, it looks like this. Okay, and this doesn't quite look like the normal distribution. If we were to actually plot, let me see if I can do lines y and exponentiate h of y, type equals L, and we'll say color equals blue. Okay, so this is the envelope function for the log PDF. Okay, and when we exponentiate that, this is kind of our actual PDF. Okay, so because we've been dealing with the log of it, just because some of the mathematical properties make it a little easier. When we exponentiate it, this is what that envelope function corresponds to. Okay, and so now we're going to take the CDF of this kind of our envelope function. Okay, and so just to kind of make our lives easier, I'm going to just say integrate. I'm telling R to integrate from -infinity up to the value that we're looking at. Okay, and so we have this function that says g plus dot CDF, and so R is just going to integrate from -infinity up to wherever it goes. And so when we integrate this, what we're going to see is that the CDF will increase, and at a certain point, once it reaches this part, what is the integral of this flat line going to look like? It's going to look linear, right? When you integrate a flat thing, the thing looks linear. Okay, so we're going to take the CDF of this thing, and it does all the calculations, and if I plot that, we can see this is what the CDF now looks like. Okay, so it goes up to a certain point, and then it becomes linear, and it goes up, and it looks like that. Okay, this is obviously different from what, if I plot p norm of y type. All right, let me see if I can do lines. Color equals, we'll do blue. Okay, so this is, the blue line represents the actual normal PDF, or normal CDF, and what we have is this crappy approximation based on our envelope function. Okay, but we have the CDF, and we can do inverse transform to generate random samples. Okay, and so we have a map from 0 to 1. If I just go back, I've got a map from 0 to 1, and what I can do is I can just propose a random uniform from 0 to 1, and then this is like a really crappy way to do it. But what I can just say is, okay, which value, like this, this is not a good way to go. But let's say I generate a random uniform and I say, okay, I get 0.342. Basically, I'm going to say, okay, which of these is the closest to 0.342? I would come up here and I'd say, okay, which of these is closest to 0.342? And I do that. Whoops. Let me see. Okay, so this is now, we're going to say u is dot last value. Okay, so I've got, which value is closest to 0.71. Using this thing, okay, it says 0.7 is the one that gives you the value closest to 0.71. Okay, and so this would be a random value, which is actually rather close to, if I say 0.71 for the p norm, it's kind of close to 0.7, right? Because this is the actual thing versus the real thing, so it's not too terrible, and we can just keep sampling this way. And again, if it gets rejected, so we calculate this, then we plug it in and we say, should we accept this value of 0.7 or not? And if it gets rejected, right? So if we generate 0.7 and it ends up out here and it gets rejected, then we incorporate that into where we should our envelope function, and we update that accordingly. Okay, and so that's adaptive rejection sampling. Yeah, we'll end here and we'll see you guys on Friday.